Hello everyone, this is Bruno from MOVEdot. Welcome to the last episode in the tutorial series where we are using VI-CarRealTime for designing a sports car together. Throughout the series, we made incremental improvements to our car while tackling a different area in each of the episodes. On episode 7, we looked at the big picture as we created an electric version of our car. Today, we'll go a step further in the development process, even beyond what's offered in the basic package of the software, as we introduce human subjective feedback into the design process. For that, we run driver-in-the-loop evaluations using a simulator, and we'll analyze each of the versions that we created throughout the design process. This is a very interesting example of how we can keep developing this project much further, still within VI-Grade's environment. Let's get it started. Cars are made for people. Whether it's using lane assist on a long trip or driving an unassisted car at the track, we interact with them in many ways throughout their life, and the quality of these interactions shapes how we judge them. We will perceive a car for things like how comfortable the ride was, how good was the feedback we got from the steering and the pedals, and how confident we felt while driving, to mention a few. What those things have in common is that all of them are subjective data and therefore difficult to collect and compare as they come, as well as hardly noticeable in offline simulations, because they're not typical numeric-based data that we can measure and use to calculate and optimize systems. Driver-in-the-loop is a simulation technique where a human can interact with mathematical models, driving them as real cars. When paired to pragmatic data collection techniques, it allows us to quantify our subjective metrics of interest and evaluate how our car is perceived by a person, even before the creation of a physical prototype. In our case, we've reached a stage in the conceptual development of our track car, where we've studied and optimized all of the systems that are most relevant to vehicle dynamics, at least in a very simplified way. But all the driving up until now was done by a robot that can perfectly find its way around any handling problems it faces and will always reach the maximum performance of whatever car and path combination we give it. Human drivers, on the other hand, despite generally being less precise, are able to deviate from the plan to investigate on the fly when they spot issues. According to the robot, we already know the car is pretty fast and balanced, so we're ready to move on and validate our model with driver-in-the-loop evaluations that shall provide us with a whole new source of inputs to continue development. To perform such tests, we need simulation software that is able to run our models in real time and physical hardware that will act as an interface for the driver to control the vehicle and get feedback from it. VI-DriveSim fulfills this role on the software side, being responsible for applying a vehicle model to the virtual driving environment and connecting the virtual controls to the physical interfaces the driver will use to operate them, like a steering wheel with force feedback. For visual feedback, we will rely on VI-WorldSim, which allows for state-of-the-art real-time rendering of models, as well as the ability to represent different weather conditions. We can display the render to multiple screens, representing the view from a driver's perspective, from mirrors, and even for each individual eye for virtual reality applications. We even can go beyond that, including equipment to represent vibrations, chassis yaw, accelerations, and many other effects, for which VI-Grade's own sim centers are prime examples that you can find and visit all over the world. The more refined and accurate is the feedback we give the drivers, the greater their immersion into the virtual environment will be. At the center of everything, there is VI-CarRealTime itself, which handles the vehicle models with all the resources that we've been exploring in this series, and is also the primary solver for our driver-in-the-loop real-time physics calculations. VI-DriveSim is compatible with many more resources for each of those functionalities, and due to its highly customizable nature, we won't get in detail about how to install and configure them in this video. Instead, we are focusing on when to use driver-in-the-loop simulations in the development process and how to implement the results of doing so in our project back in VI-CarRealTime. But first things first, let's create a driver-in-the-loop test scenario. We will be focusing today's tests on steering behavior, driver confidence, and handling under and over the limit. The test will be split in two phases. The first one will be held at VI Proving Ground, a large virtual facility for vehicle dynamics testing that includes highly detailed paved and dirt roads, differently surfaced lanes with obstacles for ride development, ramps, low mu zones, and even handling tracks. Our interest lies in the open area, a large and smoothly paved zone that we customized by adding cones and other objects to perform our low-speed stability and steering tests. The evaluation starts with 2 slaloms at increasing speeds, both below the limit, to analyze steering consistency and how the car reacts to different levels of lateral load transfer. Then, a double lane change test, also below the limit, will be used to evaluate stability and confidence based on how precise the car seems to be. The next test is focused on on-center response and feedback, both from the steering wheel and the chassis, where the car will be traveling at 130 kilometers per hour as the driver repeatedly applies small amounts of steering inputs at higher frequency. And the last test to be performed here will be an increasing speed, constant radius cornering that highlights steering characteristics at different speeds and hints at the car's steady-state limit behavior. The second phase of testing will be held at Calabogie, our development track for the whole series. Calabogie Motorsports Park is a real racetrack located in Ontario, Canada. It contains a varied layout with plenty of elevation change that should allow us to observe a car's limit behavior in many situations. There, the driver will be doing fast laps while observing balance, response, and confidence for each phase of the corner. Meanwhile, the driver will also push to observe and report on the car's behavior beyond the limit. After each test phase, the driver and development engineer review it together and fill out a subjective assessment sheet. The driver's feedback is rated for different metrics, turning their evaluation into comparable data. With such data at hand, we can take our conceptual project a little further and tune the car so that not only it is capable and balanced, like we already made sure of throughout the series, but also so that it is great to drive. Let's use this opportunity to review our development by running all of our backup models in our driver-in-the-loop evaluation program too, to see how they evolved from a human driver's point of view. This video's activities are a technical showcase, and we do not need to follow along for now, but assuming we would, to run the driver-in-the-loop tests, we first need to load up VI-CarRealTime and export our models so that they can be used in DriveSim. To do that, in test mode, locate the VI-DriveSim event in the bookshelf. Add it to a new fingerprint and select it. Here we can choose the model and the location where we wish to export it to. We can also configure more things, like what the exported model will be named, and also pre-assign a road data file adequate to the tests we intend on using it for. But we won't worry about this last one, because we can override it in DriveSim instead. Playing this simulation exports the model, and we can repeat the process to also export the other versions. The next steps are within VI-DriveSim itself, that should look similar to this when used in a single-screen desktop simulator. Here we start all the processes that will be used by the simulator, configure and load the test scenario, select one of the physical vehicle models we exported, select the road model corresponding to the scenario we configured, and click here to run our simulations. The driver can then operate the vehicle in the virtual environment as if driving a real car, performing the planned tests, each phase at a time, and debriefing with the development engineer in between them for each version of the car. Starting with the sport car example model that we based our track car on, which should offer a strong benchmark for handling. According to our driver's reports from the low-speed maneuvers testing phase, the car excelled in response and confidence. When looking at the reports from the session at Calabogie, we also see good reviews all around about its controllability in high-load situations, where the car always provided clear and consistent feedback. It was also said to feel safe over the limit, constantly presenting predictable and controllable understeer at such situations. On the downside, it was reported to be so stable that it would hinder some performance, resulting in fair scoring all around in terms of balance. All of these are traits of a well-designed sports car that is safe at high speeds. The not-so-great evaluation for balance may come from the fact that it's not specialized for dry track applications, as it should also perform well when driving in many other environments. Its average score was a 7.79, objectively showing it is a very good car. The human driver was able to lap Calabogie in 2 minutes and 9 seconds, faster than the 2 minutes and 12 seconds achieved by the robot. This difference can be attributed to the fact that max performance simulations require the robot to follow a predetermined path around the track, and the one we've used is not optimized for this specific car. The human driver, on the other hand, is able to adjust the driving line while feeling the vehicle's characteristics. The oldest track car backup model we have comes straight out of episode 1, when we began building it by installing new race-spec tires, making the body lighter, and giving it a more aggressive setup in advance, but doing all of that before performing any balancing studies. And it shows, as we could observe some unwanted behaviors during the test. The gains in lateral grip are so massive that the resulting load transfer leads to inner wheel spin under acceleration, to the point where the car is unable to reach its steady-state lateral limit in the constant radius test, because it can't accelerate past a certain speed. That happens largely because of the new and very capable tires that also led to a great increase in response. When exposed to track driving situations, the lateral load transfer can be so intense at times that the car effectively rides on the 2 outer wheels only, aggravating the traction issue even further and severely hindering control and driver confidence. In terms of handling characterization, the car was reported to feel stable at low speeds, but harshly transition into increasing oversteer beyond the limit. All of that translates into a car that, despite being much faster than before, scored a 6.33 average grade, the lowest we got. Key components like tires are powerful in scaling a car's performance, but the gains can also bring undesirable effects along, like they did here. This is common when developing a car, and a good reason to always rely on multiple ways to evaluate each step from different perspectives, like we're doing here with offline simulations and driver in the loop. Rebalancing a car to cope with new components is a must for it to handle well. And this is exactly what we began doing on episode 2, when we studied test mode and performed our first handling analysis. The changes we implemented there were enough for our driver to report that this model is once again excellent in low-speed behavior, now benefiting from the response and precision gains provided by the new tires, but in a more consistent way. It still suffers from the sudden snap into oversteer found in the previous version, but in a less pronounced manner that is easier to avoid, making it recover a bit from the very bad scoring the other model achieved in most confidence-related metrics and driving the average grade all the way up to a 7.57. Episode 3 saw the car receive another big change: the installation of an aerodynamic package together with the optimization of ride height and rake to suit it. The resulting model runs much lower than the previous ones, what should help with the load transfer issues we were facing, and together with the added downforce should increase the performance envelope a little further. And all of these things were confirmed throughout the driver in the loop evaluation. During the low-speed test phase, the driver reported the car seems more neutral and stable. At the track, the driver reported losses in response in transient situations, but mid-corner balance was improved. The most meaningful report for this model says it requires an uncomfortable, gradual increase in steering input as it approaches the limit, which seemed to aggravate even more the snapping into oversteer behavior that now feels harsher than ever and not adequate for a consumer product. Driving cornering confidence down and taking the final average score with it, that now sits at 7.31. The next backup model comes from episode 5, where we performed an extensive ride analysis to optimize the dampers. This version showed some interesting characteristics, with the driver giving it lower scores for response and consistency in the low-speed test phase when compared to the previous one, even though also reporting this new state to be more desirable than before. Side-to-side transitions were reported as if they now happen in 2 steps, an undesirable effect, but overall chassis response seems more linear with relation to steering input, which is very positive. Meanwhile, at the track, this version showed improved control in transient situations and was reported as more balanced and easier to understand, increasing driver confidence. The snap oversteer is still present, but the transition into that state is now milder. Curiously, its final grade was a 7.79, perfectly matching the score achieved by sports car. On episode 6, we redesigned the kinematics to better suit our focus on predictable, high-performance track driving, while keeping all of the previously developed parameters unchanged. The result of that was reported as a very promising car, potentially excellent in all metrics, but still hindered by that undesired behavior beyond the limit that requires the driver to constantly hold back a little and drives confidence down. Still, this version was able to improve on the previous one, achieving a final score of 7.88. Becoming our highest scoring version of the track car so far. We will continue our development by analyzing the results we got from the evaluations we performed so far, looking for the sources of the issues we ran into, and investigating solutions to extract all of the remaining potential of our combustion track car. But we also submitted the electric model for the driver in the loop evaluation, where it was reported as less responsive all around, but a bit better behaved near the limit. Driving confidence a bit up, enough to even out the score that ended up perfectly matching the best combustion model at 7.88. A very satisfying result if we remember that one of our goals when creating the electric model was to make sure it was equivalent to the combustion version. That was a lot of subjective information to process, and using it is not trivial. From observing the score progression, we can understand that the track car improved since its first iteration, a great validation for our development process. From further studying the reports, we can notice a pattern where the driver describes a persisting issue related to handling around the limit, characterized by a harsh transition into oversteer that gets progressively worse, greatly hindering confidence. This behavior was unnoticeable in the offline simulations because the robot is very efficient at driving around it. But the human driver was able to spot and describe it immediately. It highlights how powerful it is to work with both in parallel, offline simulations and driver-in-the-loop development methods. The last version of the car already has overwhelmingly positive evaluations everywhere else, and solving that handling issue will be the key to guarantee great driving experience, making our track car excellent all around. We can approach this problem from different directions. We could start by investigating rebalancing the setup towards a more understeering behavior beyond the limit, or maybe by looking at components we didn't work on yet, like the differential. But from our experience, we know such behavior is sensitive to the tire's properties, and we will begin our studies by looking at them in more detail now. The tires are the components responsible for most of the forces acting on a track car driving at the limit. Therefore, their characteristics have the potential to massively influence performance and handling. Just as an exercise, we will do a very simplistic analysis of our tires. Our car has different tires for each axle. And there is a tool within VI-CarRealTime under the Utilities menu that allows us to study them. This is what our front tire's lateral force per slip angle plot looks like at 7,000 newtons of load, which is around the maximum it experiences when running around Calabogie. And this is what the rear tire's plot looks like at 9,000 newtons, the maximum load the tires at this axle experience in the same context. We're not interested in the magnitude of these curves, but instead in their shape. If we overlay the plots, we can observe that the peak force area for the front tires is wider than it is for the rear ones. And the rear tire's force falls off faster beyond the limit. If our car is tuned to be perfectly balanced when each tire is at its very limit, but we apply some extra slip after we get there, we suddenly reach a state where the grip loss is greater on the rear than on the front, inducing terminal oversteer on a car that seemed to be neutral before the slide started. Of course, this is a really rough analysis as we're looking at a single tire at a time, instead of the whole axle, but it can already give us an idea of what to expect. Plus, it seems to match what was reported in the driver in the loop evaluations. What we are looking for is the opposite of what we have right now. We want rear tires with wider peak and milder drop after the peak, and front tires with a sharper peak. In the real world, we could benchmark other tires to find a new pairing that would provide the behavior we want, or even ask the tire supplier for a custom version that better fits those needs. In our case, we got access to the following tires that match our requirements, and we will use them in the car from now on. Along with the new tires, we also performed some differential tuning, enabled a capable ABS system, and rebalanced the car a little bit towards understeer. And you can download the new model, including all of these modifications, from the video's description to see it in VI-CarRealTime by yourself. Those modifications were enough to change the driver's perception about confidence on the car. It was reported to more safely allow for driving around the limit. What is also clear if we look at how the driver is now able to throw the car into situations that would lead to a loss of control before. The driver also noted this safer feeling came along with what felt like some performance loss, which is acceptable, but keeps the car from achieving perfect scores for balance all around. Even still, it is on par with the best scoring versions we tested before on those metrics. The final average grade for the model that was updated based on the driver in the loop evaluations was a 9.10, with a lap time of 1 minute and 45.8 seconds, the fastest we ever had. An improvement that can be mostly attributed to the car now being subjectively better to drive. In this episode, we added subjective feedback to our development process within VI-Grade's environment. We did this while studying and implementing driver-in-the-loop evaluations with VI-DriveSim to direct the next development steps, focused on making our track car great to drive. This was the last episode in our tutorial series, where we overviewed many aspects of VI-CarRealTime. We learned about vehicle modeling in the software, we studied the available test scenarios, learned about post-processing simulation results and data analysis, performed optimization investigations, and learned about vehicle dynamics conceptual project as a whole, all while developing a track car together. In a simplified world, from this point on, we could start designing and fabricating the physical components to run validation tests in real life. Or we could prefer to take a step back and try to develop everything even further, aiming at even higher scores across all subjective assessments. Or even follow your own path and redesign the car from the beginning for a whole new application. The possibilities are endless, and for all of them, VI-CarRealTime is here to help you make assertive decisions along the way. Thank you for joining us in this series. I'm Bruno Finco from MOVEdot, and I will talk to you soon.